Hello, I'm Václav Novotný, and welcome to the tutorial of Decentralized Systems 1. Today, in the first lecture, we will have introduction, then we will show how to calculate fluid properties, how to use energy balance, and how to use Qt diagrams. The content of this tutorial is to understand the principles of systems for decentralized or distributed energy systems. That means systems for power and heat or cold production, for which we will show how they look on the process flow diagrams and how to understand how they work, and how the energy is converted within them. For calculation and analysis of the potential and other parameters of efficiency or power, we will use some basic applied thermodynamics, like energy balance, which is basically just application of the first law of thermodynamics. We will look at heat exchangers, where we will apply mostly pinch point analysis, and of course most of the systems are based on thermodynamic cycles or similar calculations, so we will go through that. In this course, we will need some specific tools to do our calculations. And most importantly, for energy and thermodynamic calculations, we will need to know fluid properties. You definitely know, or you have definitely used in the past databases like steam tables or some diagrams. But here in this course, we will use a software implementation of databases, and particularly Coolprop. This database is good because, or this program is good because it's open source and it provides interface to many programs and many environments. Just for you to know, there are also other databases and programs, where the most known is RevProp from American NIST, then other, for example, FluidProp, XSteam just for water property, or there are even some mobile applications. The first thing you will need to do in this course is to download and install the Coolprop. I will show you how to do it for Microsoft Excel, which is the environment and program that will be mostly used in this course. So you can find this coolprop.org website, which is the website obviously designated to this Coolprop database and interface to other programs. And for installation, we can go to the interfaces. Then here you can see the range of the target programs, where for us probably the most important, and most of you will use Microsoft Excel, where we have directly linked to the installer. And clicking on the installer's link will forward us to the SourceForge, where we get the latest version of the Coolprop. The interface to Microsoft Excel is done already on such a level that you just install this program and you don't need to handle anything. If you would still have some problems, so you can get back to the site of the Coolprop, where there are some information regarding eventual manual installation. So you are at the Microsoft Excel, and here you eventually have a manual which you can follow. After you have the Coolprop installed, so we can go into the next part in our course. The thing you will need to understand is the Qt diagrams of the heat exchangers. It's important for fundamental understanding of processes that take place within the heat exchangers, how the heat is transferred and how eventually the phase is changed. You can see illustrative Qt diagram of a heat exchanger here on the figure, where you can see the flue gas being cooled down, while for the same amount of transferred heat, different mass flow rates of the steam or water, the water gets heated up, then evaporated, and once all steam is evaporated, it gets superheated. One of the main things of the Qt diagrams is that you always need to have positive temperature difference between the hot fluid and the cold fluid. Otherwise, the heat transfer would not be attainable. We will use this, or we will focus on this in our analysis, where we'll use so-called pinch point analysis. That means we will specify minimum temperature difference. For example, here you can see 280 and 290 degrees C. So here was definitely specified 10 degrees C temperature difference. And that's the way how we will, that's the method how we will solve our heat exchanger problems. Eventually, further on, you can have so-called UA analysis, where you know that the heat transfer equals U, the overall heat transfer coefficient, multiplied by some surface area A times logarithmic mean temperature difference. This, of course, is valid for the area where the logarithmic mean temperature difference can be defined. For example, in this case of our heat exchanger with first single phase heating up, then two-phase evaporation, and another single phase heating up of the steam, we would have to split the heat exchanger into the three parts, and for each part define this. Each part has its own logarithmic mean temperature difference. Each part has some transferred heat. So for each part can be defined the UA product. Then, in some more advanced calculation, you can have constant UA product and specify the rest of the heat exchanger based on that. Now we will go to our first example. Imagine that you have a boiler that provides a saturated steam at the pressure of 3 bar. Then this steam is throttled before being utilized in a heater, where it condenses and transfers the heat to the liquid which we want to be heated up. The properties of this liquid is Cp equals 4 kilojoules per kilogram in Kelvin, meaning slightly a little bit less than normal water. And we want to heat up this fluid from 50 degrees C to 120 degrees C, while its mass flow rate is 0.5 kilograms per second. And we want the minimum temperature difference at the cold side of the heat exchanger to be 20 kelvins. Also, we want, which is not written here, we will want the heat exchanger to be counterflow type, and the task is to determine amount of required steam, draw the heat exchanger in Qt diagram, and verify whether the minimum temperature difference in the whole heat exchanger is at all points larger than 5 kelvins. For example, here the lowest temperature difference would be 10 kelvins here. So we will have a look where is the smallest temperature difference and evaluate what value it has. So, first of all, first thing we need to do is to draw a process flow diagram. Before we get to the calculations of our examples and problems, let's look at the sign convention that we will be using. Here you can see a typical sign convention used in thermodynamics, but for us, I suggest that our sign convention will look like this. So, we will always need to look at the absolute values, and look at the direction, whether it's input or output. So we will have Q input as positive value, Q output as also positive value. Same goes for the work, and the sum will be that sum Q in equals sum Q in plus sum of the work going into the system is sum of the heat exiting the system plus sum of the work exiting the system. So in this way, we have to maybe some of you might not find it straightforward, but it helps to realize and have a proper look at the direction at which the heat and work is flowing, whether it's into the system or out of the system, and thus better understand the process. The process flow diagram for our problem is shown here. We have the boiler, which prepares saturated steam denoted as 1, which then goes through some steam line before it's throttled in this throttling valve to the point S2 at the beginning of the heat exchanger. Then outlet of the heat exchanger is noted as 5. We will see later on why we have what are the points S3 and S4. Then the working fluid, which is heated up, is denoted as F, F1 at the entry of the heat exchanger, and F4 at the outlet. Okay, now let's prepare a table where we will have the points S1 to S5 and F1 to F4, and we will have several columns for pressure, temperature, enthalpy, steam quality, and mass flow rate. First, let's start with the parameters that we know. So the steam at the boiler outlet is saturated steam at point S1 at pressure of 3 bar. So 3 bar is 300 kilopascal, and we know that the steam is saturated. So that means that the quality of the steam is 1. And let's highlight the parameters that are given. Then we know that the steam is throttled to 2 bars at the point S2. That's 200 kilopascals. Now let's write the other parameters that we know. For the fluid has Cp of 4 kilojoules per kilogram and Kelvin. So we put it somewhere here separately. 4 kilojoules per kilogram and Kelvin. Then the inlet temperature of the fluid at the point 1 is 50 degrees C. And the outlet temperature at the point F4 is 120 degrees C. The mass flow rate of the fluid is 0.5 kilograms per second. And also this 4 kilojoules per kilogram Kelvin are given. And also we had specified parameter that the pinch point at the cold side of the heat exchanger was supposed to be 20 kelvins. The cold side of the heat exchanger is obviously this one, S5, between S5 and F1. So now we can fill some other parameters in the table, because we know that the pressure at the point S3, S4, S5 will be probably the same, because there were no specified pressure losses. And then we have the pinch point 20 kelvins between point S5 and F1. So we have F1, and S5, the temperature will need to be 20 degrees C or 20 kelvins higher than this one. So it's this 50 plus minimum temperature difference of 20. So here on the left side we have the QT diagram for our heat exchanger. First, let's also mark the axis. So the y-axis is the temperature, while the x-axis is the transferred heat. Now, for the steam line, the steam enters the heat exchanger as the point S2. Like this. Now, why we left the points 3 and 4 is because those will be the points of saturated steam and saturated liquid. So here the point of saturated steam, as the steam is cooling down, will be the point S3. Saturated liquid point S4. And the outlet will be S5. Then for the fluid that is being heated up, we have the entry as F1. Then when there is transferred the same amount of heat as is between the saturated steam and the outlet, there will be the point F2. Similarly, for the point of saturated, this was saturated liquid. Here for the saturated steam on the steam side, so there will be F3, and the outlet is F4. So now we can see that between the S5 and F1 there was the specified pinch point or minimal temperature difference of 20 degrees C, but the actual minimum temperature difference will be most likely at this point between the S3 and F3. Now let's go back to our table. So now when we know that the points 3 and 4 are at saturated steam and saturated liquid, we can put these parameters in here. So the quality at the point 3 is 1 and at the point 4 is 0. Okay, now is the time when we will need to get the first I can also mark here that this temperature at the point 5 is this temperature F1 plus the pinch point, so that you can get to that back later. And now we will go to the thermodynamic parameters. So, what is the temperature at the point S1? We know that its pressure, 300 kilopascal, and we know its quality. Those are two thermodynamic properties which define the state of any fluid, at least when it has just single component. So we should be able to get the temperature. And the temperature will be a function of this pressure and of the quality. Okay, now I have extended the screen a little bit so that you can see the function bar over here. in my Microsoft Excel, and now we will start using the fluid properties Coolprop. How to do that? How to get the temperature at the given pressure and quality? We call a function which is called props SI, calling properties based on SI units, and we can click here on the function icon to get all our outputs and inputs. So the output of the function, what we want is the temperature, and now comes in the parameters on which we want to base it. So the first one will be pressure, but so we have the pressure here, but because this function wants basic fundamental SI parameters, SI units, so we need to multiply it by 1000. And the other parameter will be the steam quality, which in Coolprop has the symbol Q, and the value is over here. And finally, we need to specify for which fluid we want to get those parameters, and our fluid is water, because it's water steam. So now we will get the temperature, but the temperature is in kelvins, so we subtract 273.15 and we get the temperature in degrees C. So this is the principle how to use the Coolprop, and from now on you can use it also yourself. So this was the temperature. Similarly, we can get the enthalpy of the steam at the point S1. So again, props SI with the outlet, with the output parameter now being enthalpy, which is denoted H, and the input parameters can be again the pressure, and quality over here, and the fluid is water. Now also you see that the value is very high. It's because it's not in the kilojoules per kilogram Kelvin, but in the basic units, joules per kilogram and Kelvin. So to get these like more comfortable units, we divide the value, divide the number by 1000, and we get about 2700 kilojoules per kilogram. Sorry, here was just, it's enthalpy, not entropy. Okay, so now we have almost all the parameters at the point S1, and we can go further to the point S2. The throttling, which happens between the point S1 and S2, it's isentropic process. It's isenthalpic process. That means the enthalpy will stay the same because there is no work made and no heat transfer to the environment. So the enthalpy stays the same. Now you can see that for the point S2 we have pressure, we have enthalpy. Those are two thermodynamic parameters which define thermodynamic state, and we can get from that all the other values, which now here will be just the temperature. Now if you don't want to always use the function dialog and write the functions from the scratch for the props SE, we can use the previous function and just modify quickly the inputs. So the fluid was obviously water. We can even log that parameter by F4. Then still we will want to use the pressure, that is correct. And the other parameter will not be quality, but it will be enthalpy. And the enthalpy, as this function requires fundamental SI units, so enthalpy times 1000. So now after the throttling, the temperature is about 5 degrees C less. And it was a function of pressure and enthalpy. Now, for the point S3, again, same as at point 1, we have the pressure and we have the quality. So what we can actually do, after we log the water, we can just copy all this copy these 3 cells and directly apply them here and also here. Both cases function of pressure and quality, which we have here. The temperature is the same because we have the same pressure. It's those points are the limits of the condensation, and one's the enthalpy of saturated steam, and the other one is enthalpy of saturated liquid. And now at the point S5, which is region of subcooled liquid, we can use the pressure and temperature as 2 independent thermodynamic variables. So again, let's do it like this. So our function wants enthalpy based on pressure, which we have here, and then we will want to use temperature, and temperature is 70 degrees C plus 273.15, and we get the enthalpy at the condensate outlet. Now what to do with our fluid that we are heating up? We don't know what fluid it is. The CP is similar to water, but obviously in the problem statement the CP was provided as same throughout the whole process of heating up. But we don't know what pressure it is, at what pressure it is, so we will need to use the CP as the parameter to get the transferred heat. So because we cannot, we don't know pressure, we don't know what fluid it is, so it will be hard to define enthalpy, but we can instead of that use and define the transferred heat. So Q, or maybe let's call it delta Q. Sorry. Okay. So delta Q, and the units stay the same. And well, yeah, either we could have the lowercase q where the units would be the same, but here we will use capital Q, and it will be kilowatts. So at the start of the heat exchanger there is no transferred heat. Let's put it as given parameter. And now throughout the whole heat exchanger the transferred heat is, you have definitely seen the calorimetric equation, Q equals M times S mass flow rate multiplied by specific heat capacity times delta T. Let's use this delta so that it's clear that it's difference. So we do now the mass flow rate, we do have the specific heat capacity, and the temperature difference, we have the temperature at the inlet as well as temperature at the outlet. So M times C times delta T. So the overall transferred heat is 140 kilowatts. Now this transferred heat or this equation can be also rewritten as M times, I will use this delta H. And we can use this for our steam line. So we have the enthalpy at the inlet, enthalpy at the outlet, we have the heat, we have the transferred heat, the Q, or correctly should be Q dot, and of course M dot. So knowing this, the mass flow rate can be obtained. So the mass flow rate will be Q divided by delta H, right? So let's get directly the values. 140 kilowatts divided by enthalpy S2 minus enthalpy S5. And we get 0.06 kilograms per second or 60 grams per second, which we can see that is just a little bit less than 10 times smaller value than we have for the fluid that is heated up. Here you can see the advantage of using steam as heat transfer medium, heat transfer fluid, because you need a very small amount of it for it is transferred as gas, so quite easily and quickly within the pipes. And then when it condenses, so it releases large amount of heat. So by this we have the mass flow rate in the steam line, which was the first task that we had in our problem. And now we are still missing the temperatures at the point F2 and F3, especially at the F3, to verify the actual temperature difference between F3 and between temperatures at F3 and temperature at S3. So now how to get these temperatures. If you look at the Qt diagram, so the amount of transferred heat between point S5 and S4 is the same as the amount of transferred heat between points F1 and F2. And we know that the amount of transferred heat, same for this fluid and this fluid, is m times delta H for the steam. And m times delta H is mass flow rate of steam multiplied by difference between points S4 and S5. And we get that it's 12 kilowatts. Something similar we can do between, for example, point F1 and F3, meaning S5 and S3. So let's take the same function, just instead of S4 there would be S3. So now we get the heat transferred in each points of our Qt diagrams. Let's also finish this so that it's complete, and I have also noted, just to make it clear, I will also fill in the enthalpies here. So this was enthalpy based on pressure and quality. This was same as enthalpy S1. Here it's again pressure and quality, and here pressure and temperature. Okay, now back to the transferred heat and how to get the temperature from that. Now again, it's valid that the delta Q, let's put it like this, that the delta Q is also m Cp delta T. So if we want to get the temperature difference, maybe let's write it over here. Here, temperature difference is delta Q divided by m and Cp. Delta T is delta Q divided by mCp. And then the temperature at the point F2 is the temperature at point F1 plus this temperature difference. So temperature at point F2 is temperature at F1 plus, and now the heat transferred divided by mass flow rate multiplied by heat capacity. And we got 56 degrees C. And now let's just look this value, and this value, and we should get also the temperature at the point F3. And you can see that the heat, but you can see it also here that here is almost 139 kilowatt of transferred heat, and the superheated steam transfers just just 1 kilowatt in the whole 140 kilowatts transferred, so actually less than 1%. Which also shows that the superheated steam has quite low specific heat capacity. And now let's, however, go to our last task, which was verify if the minimum temperature difference in the whole heat exchanger is larger than 5 degrees C. So it's the temperature difference between points S3 and S3. Yes. So let's put it here. Delta T min in the whole heat exchanger. And it's the difference between points S3, 120, minus, and now F3, 119. So we can see that the minimum temperature difference is less than 1 Kelvin. In this case, definitely less than what was required. So what can we do about it? We could, for example, heat up, and what would happen in real life, we would heat up the fluid not to 120 degrees C, but to much smaller, to little bit smaller temperature. Also, what we could do, we could condense the steam at higher pressure if it would be possible, or we can have lower mass flow rate of our fluid that is being heated up. As you can see the effect of some of the changes, so for example, if we would increase the pressure to which the steam would be throttled, so changing to 250 kilopascals, we would already condense the steam at 130 degrees C and have higher temperature difference than the minimum required. Similarly, if we decrease the mass flow rate, if we decrease the mass flow rate, so it would help, but in our case we have the mass flow rate really as input parameter, which from which is derived the 140 kilowatts, which is also defining our mass flow rate of steam. So I will not show you this right away, and but what we can do is having the final temperature lower, which means, for example, just 115, and then we would have the minimum temperature difference satisfied. Now we will continue with calculation of our system, where we will have a look at the boiler. The boiler, we will consider that contains adiabatic combustion chamber, after which the flue gas has temperature of 800 degrees C, which is then cooled down as the heat is transferred to the evaporating steam, where we will require the minimum temperature difference of 50 Kelvin. This larger temperature difference is because the flue gas, the gaseous the higher pinch point is required because the gaseous phase has typically much smaller heat transfer coefficient. And what we will want to do is to estimate the stack loss and the boiler efficiency. The stack loss is the loss of the heat in the exiting flue gas, because as you will see we cannot cool it down to the ambient temperature, and how much fuel we needed if we have the fuel with the lower heating value of 12 megajoules per kilogram. So now we will extend our process flow diagram by the boiler. So this whole this bigger box is the boiler, which contains adiabatic combustion chamber where the air and fuel goes and get combusted, and the flue gas then continues into the heat exchanger where the heat is transferred to the water to evaporate, and then the flue gas exits out to the environment. So now let's add further notation to our process flow diagram and to our streams. So here we had the point S1. Let's add and let's add here the point V as water that goes in, and perhaps also 1. And for the flue gas we will have Fg as flue gas 1, like this, and the exiting flue gas will be denoted with number 3. As you might already guess why there is no number 2, the number 2 will be inside the heat exchanger. Now let's have a look at the QT diagram, how it will most likely look like. So we have the QT diagram over here, where we have the flue gas which is cooling down. Obviously the minimum temperature difference in the whole heat exchanger will be between these 2 points, because otherwise you could have case where the minimum temperature difference would be at this point, but then the flue gas would need to have extremely high temperature, which is typically not the case in any application where you evaporate the water, and the water gets heated up and subsequently evaporated to the steam. So here we had the point Fg1. This will be Fg2, and outlet will be Fg3. While with the steam we already had the S1, that is outlet of the boiler that we had before. Then let's call this point S0, and this point is inlet water W1. So now putting the new parameters and new points and streams in our table, we will extend it a little bit. So here I made space at the water side for the point 0 and for the points W1, and for the flue gas we will have flue gas at point 1, point 2 and at point 3. Now for the flue gas we will make a simplification where we will say that its properties are similar to properties of just air. Now we will insert the values that we know or that we can estimate and guess. There were not specified pressure losses. We will go through some pressure losses in the next tutorial. So now no pressure losses on the steam line. And for the flue gas, we will assume that it's at ambient pressure, which is roughly 100 kilopascals. Now the flue gas temperature is at 800 degrees C. It's over here. And as we can see from the QT diagram, so point S0 is at saturated liquid. And now for the point W1, so we will assume that it's returning condensate after going through the technology, assuming there are no other heat losses. So it will be at the temperature where it's exiting the heat exchanger, which is it's heating. So it will be this 70 degrees C. So the temperature at the point W1 will be same as temperature at point S5, because we consider that there is a closed system. So now just this was our input parameter, this was our input parameter. We can just so that our model is parametric and we can change the values. We put the other value. We put the values in the other cells as the function of the highlighted yellow ones. And one more thing that we had was the heating value, LHV, or also denoted as Qn. Of the fuel, which is 12 megajoules per kilogram. So now let's get the parameters of the fluids at this heat exchanger. So at the point 1 we have pressure, we have temperature, we can obtain the enthalpy as function of these two. So it will be like this, and for that we can directly take the function that we already had and we can check pressure, temperature goes in, parameter is the working fluid is water, and it returns enthalpy in these units. Then for the point S0, so we have pressure, we have quality. So again, enthalpy will be a function of pressure and quality as here. Let's check pressure, quality, working fluid, all valid. Now the temperature at the point 2 should be the same as this one, but just to make sure, also again as here, function of pressure and quality. Quality, pressure, we got our function. Now for the air side, we have the pressure, we have the temperature. So again, pressure and temperature are our parameters of the function to get enthalpy. We can borrow the function from the steam. Just our working fluid is not water, but it's air. Now how to get to the points 2 and 3. We can see from the QT diagram that at the point FG2 there is the minimum temperature difference. So the temperature at Fg2 will be the temperature of S0 plus minimum temperature difference, delta T. Just to make it nice, I will put the delta. Put in delta from here. And that's actually other parameter I did not specify yet in this spreadsheet, which is pinch point at the flue gas, which is 50 Kelvin. So the temperature of Fg2 is temperature T0 plus 50 Kelvin. Now we have the pressure and temperature. We can, from these two parameters, again get the enthalpy. So let's do it. Yeah, and let's move this over here because I will need space for required mass flow rate of the flue gas. So similarly, as we got the mass flow rate in here, the heat transfer divided by change of enthalpy, so it will be the same case for required mass flow rate of the flue gas to heat up and evaporate our steam. And which heat it will be? It will be the heat transferred between the points S1 and S0. S1 to S0 divided by difference of enthalpies between the points Fg1 and Fg2. Okay, so let's put it here. The heat transfer between S1 and S0 is mass flow rate of the steam multiplied by enthalpy S1 minus enthalpy S0, and now we will divide it by the enthalpy difference Fg1 and Fg2. So that is our mass flow rate of the flue gas. And now, since we know the mass flow rate of the flue gas, we can get also the remaining heat transfer between the point W1 and S0. Let's put it somewhere. Yeah, let's put it here. So heat transfer between point S0 and W1 equals mass flow rate of the steam times difference of enthalpies S0 W1, which is 14 kilowatts. Let's put it up here. And now, thanks to that we can get the enthalpy at the point 3, which is enthalpy at point Fg2 minus this heat transferred divided by the mass flow rate over here. So Q is 0 to W1 divided by mass flow rate of the flue gas. So let's put it as a value. Enthalpy Fg2 minus these 14 kilowatts divided by mass flow rate of the flue gas. And now we have enthalpy at the outlet, we have pressure at the outlet, we can get the temperature at the outlet. So the temperature at the outlet will be function of pressure and enthalpy, pH, and let's get somewhere function for temperature and modify it for what we need. So the working fluid is air, we have pressure, and now we don't have Q, we don't have the quality, but we will have enthalpy H, which is this cell G17 multiplied by 1000 to get basic SI units. And we can see that the outlet temperature will be 100 degrees C. Okay, so now we have the parameters in all the points, all the nodes of the process flow diagram. But to estimate the stack loss, to estimate the amount, to get the value of the heat that goes out in the flue gas with this temperature, we will add one more line over here, which we will call, for example, Fg0. We will say it's at the same pressure, but it will be at the temperature, which is the temperature of with respect to which is evaluated the lower heating value, which is typically 20 degrees C. So now we will get the enthalpy for that point, which will be again function of pressure and temperature. And it's the enthalpy of the flue gas, or now in our case we use properties of air, but flue gas after being cooled down to the temperature of the ambient, or temperature with respect to which is evaluated the lower heating value. And the difference between the enthalpy here and here, or the heat that could be obtained from the flue gas if we could cool it down, is in this case inevitably lost into the ambient, into the atmosphere. So we can write Q loss is mass flow rate of the flue gas multiplied by difference in enthalpies between the flue gas outlet and this enthalpy of flue gas cool down to 20 degrees C. And it's 14 kilowatts. So now, assuming that the boiler doesn't have any other loss but the stack loss, we can estimate the efficiency of the boiler. So let's call it eta B, and efficiency is always, let's efficiency is ratio of what you get compared to what you have to put in. So in our case, it's the amount of heat that is used divided by heat that has to be heat that needs to enter the boiler. So let's call it Q boiler in. Now we know that the heat that we use is the 130 kilowatts. It's the heat that is given, that the steam gives in our process, and it should be the same as, let's have somewhere here, let's have it over here. Okay. Used from the flue gas should be basically same as mass flow rate of the flue gas multiplied by flue gas inlet minus flue gas outlet. It's roughly the same as this 130 kilowatts. The difference is mainly caused by the fact that we transfer the heat to the steam or to the water at elevated pressure, and we excluded in the overall balance the pump work that pumps it back from 200 kilopascals to 300. So that would be the remaining part of the heat. So we have Q used, we have Q lost. Now let's get the inlet of the boiler. Let's say BS, boiler in. The heat that goes into the boiler needs to be the heat that goes out. And what goes out? First, this part that is used, and second, this loss into the atmosphere. So that's 144 kilowatts, and the efficiency of the boiler is then Q used 130 divided by what goes into the boiler. And from this we get that our efficiency is roughly 90%. Okay, and the last task was to estimate how much fuel is needed. So the lower heating value of the fuel is 12 megajoule per kilogram. So the mass flow rate of the fuel, let's put it here, is the heat that needs to go into the boiler. And now we can divide the heat by 1000 so that we get megajoules. So megajoules divided by megajoule per kilo, and megawatts divided by megajoules per kilo, and we get kilograms per second. So 0.012 kilograms per second of the fuel. Okay, so that's it for today's problem. See you next time.